Yes, effective permittivity, you betcha. What else? Rhymes with relific meat capacity.
So,
Capacity?
specific heat.
Specific heat capacity.
Is this,
So there's a lot of things going on here. I know, that was a stupid. Touchdown, double take, right? Discount double take. Well, Montpellier flat. So, what do these constants all have in common? Emissivity is probably the least obvious, but what do they all have in common?
Greek letters?
A for the day. What else do they have in common? Because they're intrinsic physical properties, surprisingly, they're temperature dependent.
I was gonna say resistivity's gotta be temperature dependent.
They are
It's a
all
superconductor.
temperature dependent, intrinsic
Yeah.
physical properties, and just about every physical property, even length and surface area, pretty much anything that you can measure is temperature dependent. So let's just make a note here. First of all, the rho is temperature dependent. And as much as I hate this first order approximation, we typically say that the resistivity at any particular temperature can be calculated or determined by looking at the resistivity at some reference temperature times the factor of 1 plus. Here's another Greek character. Here's another physical property that's also temperature dependent, even though we don't look at it in terms of temperature dependency. This is the thermal resistivity constant, coefficient of thermal resistivity, times the difference in temperature between the reference temperature and the temperature that you're comparing it to. Now, if you stare at this quickly, it looks awfully similar to a Taylor series. It's a first order approximation. It's an exponent, an exponential relationship that as long as you look over fairly small delta t's, it's approximately a linear relationship, but it's not really. But this is, to a first order, how temperature is related to resistivity, assuming you know a reference temperature. So, and by the way, this is very similar to calling the specific heat capacity 1 for water and then measuring heat capacity of other things in a calorimetry experiment. You just know what 1 is and you can compare everything to that. So,
What was the new symbol? Sorry, I skipped up.
alpha.
What is it?
Now the units of alpha are inverse Celsius or inverse Kelvin, because this is a unitless quantity in the parentheses. All these damn engineering constants.
Oh.
So, and either inverse Celsius or inverse Kelvin. It doesn't matter if you're taking a delta, so Celsius is usually the easiest. Okay, so first of all, what that tells you is for any substance, this ratio is not necessarily a constant quantity. It's only constant to the extent that this term is small. Otherwise, nothing is truly constant. So that's the first thing. A couple other things about alpha. Alpha is positive for conducting materials, metals, for instance, highly conductive materials. And it's a negative number for semiconducting, and more in particular, non-conducting, insulating materials. There's no such thing as a non-conductor. The question is, how much potential difference in how much energy and force is necessary to physically push an electron off of something. Right? Given enough energy, you can yank an electron off helium, which is the most tightly held electrons are on the helium atom. So I guess I should mention that. So alpha is greater than 0 for metals, and alpha is less than 0 for insulators or nonmetals. I'll say nonmetals, but it could be something that's more composite as well. And that's important because what it means is that when metals get hot, the resistivity and the resistance goes up. When nonmetals and insulators get hot, this one kind of makes sense. You're shaking it so much, it's a lot easier to get the electrons off. But when you have a conductor and the electrons already come off easy, the more you thermally agitate, the more barriers you put in front, the harder it is to push those electrons through. So for opposite reasons, increasing temperature allows charge to flow more readily through non-conducting materials, and vice versa for metals. Now, the next point I wanted to make is that when the ratio of V1 over I, which is resistance, when this is constant over a range of delta T, we call it an ohmic material. So when we say it's Ohm's law, this is a linear ratio of V over I is constant. That's an ohmic. So half of electrical circuitry is combining ohmic materials with those materials that are not ohmic. So when delta V over I is not constant, it's called a non-ohmic. It's just a nomenclature, but a non-ohmic substance. So semiconductors, doped germanium, doped silicon, phosphorus, doped germanium, all of these things that are not, that do not have a constant resistance or a constant voltage to current relationship, even over small temperature ranges, those substances are the non-ohmic substances. We make diodes, transistors, out of those materials. Where we use constant resistor materials, or carbon resistors, if you will, to control current flow. So the action happens with non-ohmic materials. Ohmic materials we use to control our current flows. You sort of see where the process comes in, why we use one over another. Non-ohmic materials are much more dynamic. Okay, so those are really the three big pieces to how this charge flow is related. Now, I want to go back to this little conductor model for a second. Okay, so this has a resistance. I have no idea what the resistivity is for copper or something like that. But we could say that the resistance of this thing should be related to whatever this resistivity constant is, times the length of this thing, and inversely related to the surface area. Now, that being said, what if we split this thing into two little slabs? And let's do this horizontal slice. Everything you need to know about resistors we can look at and think about in these terms. So here's one slab, same length, and and it's gonna have a surface area of 1, A1. What would the resistance be for this thing? Symbolically. Well, if it's exactly half, it would be double. But regardless, it should be related to the same resistivity, which does not change with dimension, only material, times the length, and inversely related now to A1. The second slab, I'll make it a little bit larger. Where's TU when I need it? A2, same length L. We could write the resistance of this slab as resistivity times L over A2. Is that reasonable? So, this resistance and this resistance. How are these resistances related to this resistance?
Additive.
We might note that A1 plus A2 is equal to
I agree.
a total A, total, right?
So they've gotta be the sum of the inverses, the inverse of the other one.
Yeah. So if we just added R1 plus R2, we would get rho L A1 plus rho L A2. This does not equal rho L A1 plus A2. Agreed? However, let's just also observe that 1 over R is related to rho, or A divided by rho over L. This quantity can be expressed as rho, as A1 over rho over L plus A2 rho over L. Which is just another way of saying the inverse of the resistance here is related to 1 over the resistance of the thin slab plus 1 over the resistance of the other slab. Counterintuitive. Counterintuitive. This may harken to equivalent resistance with parallel connected circuit elements, resistors. Note how organic it is. You can think about it in 15 different ways. But the easiest way to think about it is just cut the damn thing in half and look at how the resistances ought to be. So, in other words, what this says is that the R1 and R2 slabs are arranged parallel to each other. And if this is R1 and this is R2, if we connected them so we could run a positive voltage across them with respect to the other end, then the total current that flows between I1 and I2 is related to I2, R2 is V, I1, R1 is V. Equivalent resistance between R1 and R2, the inverse inverse of that is equal to R1 plus R2. Between the two sides, the two endpoints. Now, think about the opposite, and this one is very little information. And then you want to do some problems, you want to stop looking at this shit, you want to see some real numbers and put it all together. I know, I've heard the news. We split these things into vertically. Now we would have same cross-sectional area with an L1, okay, and an L2 and an L. The resistance of this first slab should be related to rho L1 over A. The resistance of the second slab should be rho L2 over A. And if you added them together, lo and behold, they equal rho total length over A. So here's your consecutive or series arrangement of conductive materials. So R1 plus R2 is rho L1 plus rho L2 over A. And L1 plus L2 is the total length L. So R1 plus R2 should be equal to rho L over A, which is equal to the original R. This is essentially the phenomenon where you have series arrangements of conductors. So we'll just note R1 and R2 are arranged in series. Again, this was one that, rather than deriving it from Ohm's law on an electric circuit, I really appreciated when I took physics actually saying sort of geometrically why and how these things ought to be the way they are. So whether it's more time consuming or not, or less practical, that's a separate question, but for me this is important. Now, let's put these pieces together. And this is a way, way overestimate, but okay. Take a light bulb. At room temperature, so at about 25 Celsius or so. It's not really room temperature. For bulb 1, the resistance at 25 degrees Celsius is 3 ohms. Its length and its area. Its area is pi times 5 times 10 to the negative 6 meters squared. 5 micrometers. And its length is 8 centimeters.
Really a bulb, or is this like some kind of fiber optic thing?
It's 8 centimeters.
Long and super skinny.
It's
8 times 10 to the negative, oh, meters, yes.
Yeah, let's go with meters.
Tried to convert it for you, I should just leave it alone, damn it. Okay, so what would the resistivity of this particular substance be? Sorry, 6. See if I can find a resistivity value. Probably look it up on my phone. Here we go. So what do we get for a resistivity? Ten to the negative 9?
Let's see here. Ourselves.
And, so the 3 ohms divided by the length times the area, or you have the.
3 ohms times the area divided by the length.
Yep.
Yeah.
Okay, so I'm cheating on you.
Negative nine.
This is a 5.
We just built up a great relationship.
I know.
Negative 5. That makes it.
Negative 5.
That just changes.
2.31 times 10 to the negative 7.
So you just.
No.
No, 2.95
Yeah.
times 10 to the negative 7.
Oh,
Okay. So rho is,
nine.
at this temperature,
Composition.
is 2.95 times 10 to the negative 5th?
7.
7, okay. And the units of this ought to be? Ohms per meter.
Ohms. Would be.
Now, what's that?
Isn't it ohms times meters? You got area in the numerator and length in the denominator.
R.
Yeah, so you multiply by area. So that's.
R times. meters
Oh, I'm
squared
thinking
divided by
about them
meters.
backwards, yes, all meters, sorry. I'm looking at the A and the L. I know, I just keep ruining it. Blame it on the platform. Okay. So. What did I say alpha? I didn't give you a value for alpha, did I? So let's make alpha about 7 times 10 to the negative 3rd per degree Celsius. When the resistance of this bulb is 15 ohms, what is T? And we'll assume that area and length are not significantly changing. So we know that's fake.
All models.
Yeah, that's right. Every model is wrong.
Well, some are useful.
Yeah, some are useful.
So you get through that one and figure out the temperature. What's the drift velocity at that temperature?
Two point
So what
seven
is our
four
alpha value?
times 10 to the negative
7.0 times 10 to the negative 30. Plus, not minus.
No.
You didn't? So you use a delta T of negative 10?
Times 10 to the negative 30.
Who's got numbers to compare to my numbers? Anybody?
Almost there.
Okay.
So, and by the way, if L and A are constant, then I'm going to take a shortcut approach, and rather than use my resistivity, I'm gonna make a note that R over R naught, the A's, the L's, and the rho's all cancel. Should be equal to 1 plus alpha T minus 25. It's kind of dirty cheating on my part, but I can do that. In other words, I can calculate the rows. The ratio of the rows would look the same way, but for the same A and the same L, why bother? So to this end, then, we've got T should be R over R naught minus 1 divided by alpha plus 25.
No, what?
Or, let me see, was it 3 to begin with? It's 15, so it's 4 divided by, and this would be in units of Celsius plus 25. So, 600 Celsius?
596, yeah.
And that's plus the 25, right?
Yes, correct.
It's only off by about 700 Celsius, but it's close enough. I don't like that approximation. It only works for small hundreds and tens and 5, 10 degrees only. Okay. So, how are we gonna do the second bolt? When the second bulb is attached, combined current across both bulbs. .5 amperes. using the same power supply. As in 3. How are the bulbs connected? What is the resistance of bulb 2? And that's probably enough for now. Okay, so some conceptual and some physical. So first of all, how are these bulbs connected? You got 2 bulbs. How are they connected? If they're in series, what's their resistance going to do? Is it going to be additive, or is it going to be inversely additive? Additive. So is the resistance going to be higher? Is the resistance higher or lower when you have the second bulb added?
Higher.
Current is higher, so the combined resistance is lower. We had 0.3 amperes, now we've got 0.45 amperes. So I was trying to get a conceptual point across here. So if I've got a bulb, now let's make the picture here, and everything else notwithstanding, I've got a power supply, and I've got my R1 bulb here. And I know that I've got 0.3 amperes across this bulb.